In this problem, we are given a vector field, f of x, y, z equals y squared, sine z is your first component, 2xy sine z is your second component, x times y squared cosine z is your third component. You have a vector valued function, r of t, equals t squared I plus cosine tj plus tk. T goes from 0 to pi. Now, we actually want to avoid evaluating the line integral with respect to the vector field directly. That's the hard way. We want to use the fundamental theorem of line integrals. But in order to do that, we need a potential function for our vector field, so that when we take del of our potential function, the gradient of our potential function, we get f, right? So here's what we want. We want little f of x, y, z. That's a scalar function, such that del little f is equal to capital F, the vector field. But remember, del little f has components f sub x, f sub y, f sub z. That's the definition of the gradient. Remember that? So what does that mean? That means that if this little f exists, it doesn't always exist, but if it does, that means y squared sine z is the partial of little f with respect to x, if the potential function little f exists. That means that the component of j is little f sub y, or the j component, I should say, and the k component is f sub z. So what that really means is if we integrate f sub x, y squared sine z, with respect to x, we can recover within a constant. We can, a constant with respect to x, we can recover little f. But then we have to figure out what that constant function is in terms of y and z. So that's where the difficulty lies. So are you with me if I say f of x, y, z should equal the integral of this component with respect to x? Does that seem reasonable? Okay. Well, what's the integral of y squared sine z dx with respect to x? It's like a partial integration, right? A partial antiderivative, right? It's just x times y squared sine z, because y squared sine z is a constant with respect to x. Plus what? So x times y squared sine z plus some function. It's got to be a function of y and z, right? Because those are constants with respect to x. So plus, let's use g of yz. But in order to find the potential function, we need to know what g of yz is. Okay, but we haven't made use of the second component of the vector field or the third component yet. So what we can do now is, okay, this guy is a representation for f of x, y, z, little f. But can't we take the derivative with respect to y and set it equal to the j component of the vector field? Shouldn't that be f sub y? Okay, so the thing we just found, let's take the derivative with respect to y. What do we get? So it's x times y squared times sine z. X and y and x and sine z are constants with respect to y. So what do we get? 2xy sine z plus
g sub y.
There you go. The derivative of g with respect to y, right? And what do we set that equal to?
2xy sine z.
Okay, so 2xy sine z. Does everybody see where that's coming from? It's coming from this guy, right? Okay, so focus on this equation. What happens if I move the 2xy sine z from the right side to the left side by subtracting it? What's left?
G sub y equals 0.
Yeah. So that all that means is the derivative of g with respect to y is equal to 0. So all that means is g is does not involve y, right? It could still involve z, couldn't it? Because with respect to y, z is a constant. So g of yz can be thought of as a function h of z. Because if its derivative with respect to y is 0, then there is no y in g. So it's a function, at best it's a function of z, just z. Does that reasoning seem reasonable? Is that okay? So now I can rewrite f of x, y, z as x times y squared sine z g of yz turned out to just be a function at best of z.
Wait, so you just picked h as just like arbitrary?
Yeah, it's just, I'm just trying to rewrite it in a simpler form. Yes. Does everybody believe that? Now there's one thing I haven't made use of yet. I need to find out what h of z is. What haven't I made use of?
F sub z.
This third component, right? So the third component I can get by taking the derivative with respect to z of f. So f sub z of x, y, z. Okay, what do you get when you look at this formula and take the derivative with respect to z?
X, y squared cosine of z.
Times, or plus rather.
H prime of z.
Yep, you can use the prime notation here. And then you set that equal to the third component of your vector field, which is x, y squared cosine z. And what do you find out from that? Well, yeah, you do get these guys. If you subtract them, you get h prime of z is equal to 0, which means h of z is a true constant, right? So you could conclude from that, you can conclude that h of z equals a constant. What do you want to call it? C? K? All right, a constant. K, a true constant. So I suppose you could say that f of x, y, z is equal to x squared. No, I'm sorry, I wrote that wrong. X, y squared sine z plus k. But remember what we're trying to do. All we really want is a potential function so that we can apply the fundamental theorem. If you go back to this problem, we want to find f and use it to evaluate the line integral with respect to the vector field. So we really don't need that constant for that, because when you apply the fundamental theorem, the constants would just cancel out. So to evaluate, you could consider this your answer if all you were doing was looking for f. But we'll take k equal to 0 to apply FTLI, the fundamental theorem of line integrals. And so that means we'll use f of x, y, z equals just x, y squared sine z. So we've got our potential function. So remember what the fundamental theorem of line integrals says. It says you can take f of the endpoint minus f of the beginning point, and you've evaluated your line integral over the vector field, right? In other words, the line integral with respect to the vector field is independent of path. So all we need to use R for is to find the beginning point and the end point of your parameterization, of your curve, essentially. So here's R of t. What's the beginning point going to be given by? So R of 0 would be your beginning point, right? That's where the lower value on t. R of 0 equals, well, what does that equal? Well, if you plug 0 in here and square it, you get 0, right? 1 and 0. And what does, t equal pi, R of pi look like? pi squared, comma, -1, comma, pi. All right, so let me take these guys with me. To finish up the problem. So this is the beginning point. Well, if you just think of the ordered pair at 0, 1, 0, that's your beginning point or starting point, either way. Beginning point. Pi squared, -1, pi is your end point. And we know from the fundamental theorem of line integrals that the integral over the vector field represented by this symbolism is simply going to be little f of the endpoint minus little f of the beginning point. Does that make sense? So that means f of what minus f of what?
Pi squared, -1 pi minus f of 0, 1, 0.
Yeah, so pi squared, -1 pi would be, whoops, pi would be your endpoint, f of your endpoint, and then f of 0, 1, 0. That's f of your beginning point. Okay, what was f again? F is this beautiful thing, right? So what do we get? Okay, x times y squared, what would that be? That would just be pi squared, wouldn't it? Times sine of z. What's sine of pi? 0. So just 0. Minus, well, what happens if we put in 0 here? 0. So you get, everything zeroes out? Yeah.